Most so-called STEM toys for 10-year-olds teach kids how to play games inside a closed ecosystem, not how to write real code or design actual parts. My name's Rajiv Patel, and after 15 years building systems that connect hardware and software in enterprise environments, I've spent the last several years translating what companies actually hire for into skill-building paths that start early. Today, we're walking through the products that teach 10-year-olds legitimate, transferable technical skills, the kind that show up on job descriptions, not just toy packaging.
You're listening to the STEM Lab podcast. Quick heads up before we dive in. Everything you're about to hear, the research, the analysis, the script, is 100% human verified and written by real authors with real expertise. The voice you're hearing, though, that's AI generated. Just wanted to be upfront about that. If you've been listening for a while, I really appreciate you being here. And if you're new, welcome to the show. We drop new episodes every Monday, Wednesday, and Friday, covering everything from product recommendations to skill-building frameworks that actually matter. Now, here's what we've got for you today.
STEM toys for 10-year-olds that teach real skills should prepare learners for actual industry tools, not just entertain them. At age 10, children can master text-based programming foundations, CAD workflows, circuit logic, and prototyping skills that directly translate to employable capabilities. This guide identifies products that build measurable competencies aligned with current hiring requirements in engineering, software development, and technical design roles. Now, let's talk about what we mean when we say real skill STEM toys. These function as training platforms for industry-standard tools rather than simplified analogs. They introduce learners to authentic workflows, Python syntax, Arduino IDE environments, CAD software interfaces, and circuit debugging protocols, using age-appropriate scaffolding that removes complexity without diluting methodology. The distinction matters in measurable outcomes. A block-based visual programming toy might teach conditional logic, sure, but a true skill-building platform teaches conditional logic while introducing Python syntax that transfers directly to professional development environments. According to IEEE Spectrum's 2025 programming language rankings, Python remains the most in-demand language for embedded systems, data science, and automation engineering, making early exposure to text-based Python syntax a defensible investment. So what are the key characteristics? First, direct progression to professional tools. Products must create clear pathways from learning platform to industry software, Scratch to Python, Tinkercad to Fusion 360, visual circuit builders to actual breadboard prototyping. Second, offline capability. Cloud-dependent platforms create project continuity risks and lock learners into proprietary ecosystems. Third, expandability. Hardware should accept standard components like Arduino-compatible sensors, industry-standard filament, modular mechanical elements. And fourth, no consumable dependencies. Products requiring subscription content or proprietary refills fail the long-term ROI. The 10-year-old developmental window represents peak readiness for abstract reasoning and algorithmic thinking. Learners at this age can debug multi-step programs, interpret technical documentation, and iterate on design failures, capabilities that justify introducing authentic engineering constraints rather than gamified simulations. Moving on to how these skill-building products actually work at age 10. They operate through what I call progressive disclosure of complexity, exposing learners to professional-grade tools through structured learning paths that gradually remove training wheels.
Let's start with programming platforms. Text-based coding platforms for this age group typically follow a three-stage progression. First, visual-to-text hybrid interfaces. Tools like the Sphero RVR Plus programmable robot provide block-based programming with simultaneous Python code display, allowing learners to correlate visual logic with actual syntax. Second, guided text environments. IDE platforms with autocomplete, syntax highlighting, and contextual error messages reduce cognitive load while maintaining authentic coding practices. Third, standalone project execution.
Learners write, debug, and deploy code that controls hardware outputs without intermediate translation layers. The Arduino Starter Kit Official demonstrates this model effectively. Check the link below to see the current price. Learners progress from uploading pre-written sketches to modifying function parameters to writing custom sensor response logic. The Arduino IDE provides real compiler feedback, actual error messages referencing line numbers and syntax violations, teaching debugging methodology used in professional firmware development. It's compatible with Windows, Mac OS, and Linux, has no cloud dependency, and you can expand it with any 5-volt compatible sensors and shields following standard pinout specifications. In terms of practical specs, you're looking at a USB-B cable connection, 9-volt battery or 7 to 12-volt DC power, and the breadboard accepts standard solid-core wire. The component sockets have been durability tested through over 500 insertion cycles. One friction point worth mentioning: Arduino's C++ syntax introduces pointer notation and memory management concepts that create steeper learning curves than Python. This trade-off delivers transferable embedded systems knowledge, but requires more patient instruction than higher-level languages. Now let's talk about CAD and prototyping systems. 3D design platforms for 10-year-olds should introduce parametric modeling concepts, dimension-driven design where changing one measurement propagates through an entire model. This workflow mirrors professional CAD practice in mechanical engineering and industrial design. Tinkercad provides appropriate entry-level parametric tools with constraint-based modeling, but learners should transition to Autodesk Fusion 360, which has a free educational license, within 6 to 12 months to access timeline-based editing, engineering simulation features. The Creality Ender 3 V3 SE offers a practical output platform. Check the link below to see the current price. Auto bed leveling reduces setup friction, the open filament system avoids proprietary consumables, and the build volume accommodates functional prototypes at 220 by 220 by 250 millimeters.
For practical operation, you're looking at 220 watts of power consumption, a heated bed that reaches 100 degrees Celsius in 5 minutes, and it accepts standard 1.75 millimeter PLA, PETG, or TPU filament. The Bowden extruder requires 4 millimeter retraction settings, and you can expect the nozzle to last 200 to 300 print hours before replacement. The Ender 3 V3 SE's open frame design creates thermal management challenges with ABS printing. Warping occurs without enclosure modification. For households prioritizing plug-and-play operation over learning thermal dynamics, this represents a legitimate drawback. Next up, electronics and circuit logic. True electronics skill building requires breadboard prototyping with actual components, not snap-together modules. The Alegu Electronics Component Fun Kit supplies discrete resistors, capacitors, transistors, and ICs. Check the link below to see the current price. Learners must calculate current limiting resistor values, understand voltage divider circuits, and interpret component datasheets. This introduces failure modes absent from modular systems: reversed LED polarity, incorrect resistor calculations causing component burnout, floating input pins producing erratic behavior. These failures teach troubleshooting methodology and circuit analysis that transfer to professional PCB design and embedded systems development. The components are rated for 5-volt logic levels, quarter-watt resistors handle Arduino output current, LEDs require 150 to 330 ohm current limiting, the breadboard is rated for 1 amp maximum current per rail, and storage in anti-static bags extends component lifespan beyond 10 years. So why does real skill STEM investment matter for 10-year-olds? The labor market increasingly demands technical literacy across all professional roles, not just engineering positions. GitHub's 2025 State of the Octaverse report identified Python fluency as the second most requested skill in job postings across finance, healthcare, and scientific research sectors, disciplines traditionally disconnected from software development. Starting skill acquisition at age 10 creates 6 years of compounding capability development before college applications. A learner who begins Python at 10 can reasonably achieve intermediate competency, writing classes, implementing algorithms, using third-party libraries by 13, then spend 3 high school years building portfolio projects that demonstrate employable skills. This timeline matters. College admissions increasingly weight demonstrated technical capability over standardized test scores, and internship opportunities in software and engineering fields now target high school juniors with existing code portfolios.
The financial argument holds equal weight. STEM toys for 10-year-olds that teach real skills represent one-time capital expenses that deliver multi-year utility. An Arduino kit purchased at $90 provides hardware for 4 to 6 years of progressive projects as the learner's software skills advance. Contrast this with gamified coding subscriptions at $20 to $40 per month. Over 5 years, subscription costs accumulate to $1,200 to $2,400 with zero residual value and no transferable skills beyond platform-specific puzzle solving. Let me outline the skill gaps addressed by age-appropriate tools. Current STEM education suffers from 3 systematic failures that quality products can remediate. First, abstraction without implementation. Many school programs teach algorithmic thinking through unplugged activities, but never connect these concepts to executable code running on real hardware. Second, visual programming cul-de-sacs. Block-based environments that fail to provide explicit pathways to text-based languages leave learners stranded when they outgrow visual interfaces. Third, consumer-grade fabrication without engineering principles. 3D printing activities that treat printers as magic boxes instead of teaching material properties, thermal dynamics, and mechanical design constraints. Products that address these gaps share common characteristics. They expose underlying technical systems, require learners to consult documentation, and produce tangible failure modes that demand systematic debugging. Now let's talk about career pathway alignment. 10-year-olds learning with appropriate STEM toys develop capabilities that map directly to entry-level technical competencies in multiple career paths. In software development, that's Python syntax, version control concepts through documented project iterations, API interaction through hardware libraries. In mechanical engineering, CAD parametric modeling, tolerance analysis through print, fit, test cycles, material selection based on mechanical properties. In electrical engineering, circuit analysis, component datasheet interpretation, signal logic debugging. In data science, algorithm implementation, sensor data collection and visualization, statistical reasoning through experiment design. I ran both my children through Arduino to Python progressions starting at age 10. By 13, both could implement basic machine learning models using Scikit-learn, not through memorization, but because they understood function syntax, data structures, and library documentation navigation from years of accumulated practice. This represents measurable capability development impossible to achieve through gamified platforms or closed educational ecosystems. Let's break down the types of real skills STEM toys for 10-year-olds. They fall into 5 categories, each developing distinct but complementary competencies. First, text-based programming platforms. Hardware that requires actual code, not visual blocks, to function. The Raspberry Pi 400 personal computer kit provides a complete Python development environment in a keyboard form factor. Check the link below to see the current price. Learners write scripts that control GPIO pins, process sensor data, and interact with web APIs. It's compatible with any HDMI display, runs Raspberry Pi OS, which is Debian Linux, and includes Python 3.11, Scratch, and Thonny IDE pre-installed. You get 4 GB of RAM, a quad-core ARM processor, a 40-pin GPIO header, USB-C power at 5 volts 3 amps required, micro SD storage expandable to 256 gigs, no forced cloud connectivity, and USB 3.0 ports that accept standard peripherals. The Pi 400's ARM architecture means x86 compiled binaries won't run. This occasionally creates compatibility issues with specialized scientific libraries, though most Python packages now support ARM through pip installation. Second, CAD to manufacturing workflows. Tools that connect digital design directly to physical prototyping. Entry-level 3D printers should accept G-code from any slicing software, Cura, Prusa Slicer, Simplify 3D, rather than requiring proprietary ecosystems. This teaches learners that CAD to slicing to machine operation represents a universal workflow across all CNC manufacturing, not just hobbyist 3D printing. Third, electronics prototyping systems. Breadboard-based kits that use discrete components rather than pre-assembled modules. The distinction matters. Snapping together proprietary sensor modules teaches spatial assembly, but not circuit analysis. Placing individual resistors, calculating voltage drops, and measuring current flow with a multimeter teaches transferable electrical engineering methodology. Look for kits that include data sheets and component specifications rather than just pictorial assembly guides. Learning to interpret voltage-current curves, maximum ratings, and operating temperature ranges introduces technical literacy skills used throughout engineering careers. Fourth, robotics integration platforms. Systems that combine mechanical assembly, electronics, and programming in open architectures. The VEX Robotics V5 Classroom Starter Kit demonstrates proper integration. Check the link below to see the current price. It's programmable with text-based C++, the modular aluminum structure accepts custom-designed components, and motor controllers provide PID tuning parameters for advanced control theory exploration. The V5 Brain runs VEX RTOS, has a 480 MHz ARM processor, 11 motor ports, 21 megabits per second wireless download speed, a rechargeable 1100 mAh battery, and it's compatible with VEX code in either block or text. It supports Python and C++.
VEX's ecosystem cost adds up quickly. Additional sensors and actuators carry premium pricing compared to Arduino-compatible alternatives. This trade-off buys mechanical durability. The aluminum structure survives competition-level stress, and you get comprehensive documentation, but it creates cost barriers for extensive customization. Fifth, advanced maker tools. Oscilloscopes, logic analyzers, and precision measurement instruments scaled for educational use. The DSO-150 Digital Oscilloscope Kit requires assembly, learning to solder SMD components, and calibration, then provides waveform visualization for debugging circuit timing issues. Check the link below to see the current price. This introduces signal analysis methodology used in professional electronics development, RF engineering, and automotive diagnostics. You get 200 kHz bandwidth, 1 megasample per second sampling rate, 0 to 30 volt input range, calibration requires a 1 kHz square wave source, and SMD soldering requires a temperature-controlled iron and magnification. Now let's talk about progressive learning path integration. STEM toys for 10-year-olds that teach real skills should slot into multi-year progression frameworks rather than function as isolated activities. The optimal pathway follows this sequence. Year 1, age 10, visual to text hybrid programming like Sphero with Python display, Arduino with Blockly transition to sketches, Tinkercad CAD basics, breadboard circuits following detailed schematics. Year 2, age 11, text-based Arduino programming with custom functions, Fusion 360 parametric modeling, circuit modification, and component substitution. Year 3, age 12, Raspberry Pi Python projects with external libraries, CAD to print integration for functional prototypes, PCB design in KiCad. Year 4, age 13, advanced Python, including classes, file I/O, API interaction, multi-component assemblies with engineering tolerances, microcontroller programming in C. This progression ensures each skill layer builds on established foundations while introducing professional-grade complexity. Let me give you some cross-domain project examples. Real skill development accelerates when projects integrate multiple disciplines. An automated plant monitoring system. Python script on Raspberry Pi reads soil moisture sensors, that's electronics, triggers servo-controlled watering mechanism, that's mechanical design, logs data to CSV for analysis, that's programming, uses 3D printed sensor enclosures, that's manufacturing. A custom game controller, CAD-designed enclosure, Arduino Leonardo emulating USB HID device, debounced switch circuits, Python configuration utility. A weather station, circuit designed for temperature, pressure, humidity sensors, outdoor rated enclosure design, data visualization dashboard, solar power system integration.
These projects require learners to debug across multiple failure domains simultaneously, a skill directly applicable to systems integration roles in enterprise technology environments. Let's talk about lab infrastructure requirements. Effective STEM skill development demands dedicated workspace with appropriate infrastructure. Minimum requirements start with power. You need a dedicated 15-amp circuit with surge protection, multiple outlet access for simultaneous device charging, circuit breaker accessible in case of short-circuit scenarios during prototyping. Ventilation matters. 3D printer operation requires air circulation. PLA emits ultrafine particles. PETG and ABS require active ventilation, and electronics work benefits from a dust-free environment. Storage. Component organization systems for resistors, capacitors, ICs with labeling, filament storage in sealed containers with desiccant, project-in-progress space that doesn't require daily teardown, safety equipment, safety glasses for breadboard work because component leads are under spring tension, fire extinguisher rated for electrical fires, first aid kit, proper lighting, minimum 500 lux task lighting for detail work. Now for budget allocation strategy. Initial equipment investment for real skill STEM learning typically falls between $400 and $800. A programming platform like Raspberry Pi 400 kit runs about $100, or Arduino starter kit plus laptop is $90 plus your existing computer. A 3D printer, entry-level FDM, $200 to $300. Electronics components, including breadboard kit, multimeter, basic toolset, about $100. CAD software is free, Tinkercad, Fusion 360 educational license, consumables like PLA filament, hookup wire, LEDs, and resistors, $50 initial supply. This investment supports 3 to 4 years of progressive skill development before requiring major upgrades. Contrast with subscription-based educational platforms at $30 to $40 per month, accumulating to $1440 to $1920 over 4 years with zero residual hardware value. Let's talk about evaluating product claims versus actual skill transfer. Marketing materials for STEM toys frequently overstate educational outcomes. Here are filters to apply when evaluating products. Red flags indicating limited skill transfer. Age ranges spanning 5+ years, like 8 to 14, suggest content neither challenging for older learners nor appropriately scaffolded for younger ones. No coding required positioning for robotics products, removing programming removes primary transferable skill. Proprietary app ecosystems with no API documentation or export functionality. Marketing emphasis on fun and engagement without specific capability outcomes. Absence of compatibility specifications like supported operating systems, required software versions, hardware expansion standards. Green flags indicating legitimate skill building. Explicit compatibility with industry-standard tools, Arduino IDE, Python 3.x, STL file format, standard electronic components, published API documentation and community code repositories, clear progression pathways to professional software like Blockly to Python, Tinkercad to Fusion 360, offline functionality with optional cloud features rather than cloud dependency, user-accessible technical specifications including processor speed, memory, I/O capabilities, power requirements. Now, subscription services versus one-time purchases. Monthly subscription boxes for STEM education create ongoing costs without building reusable infrastructure.
The value proposition only holds if projects introduce genuinely new skill domains each month, not variations on existing capabilities. Materials accumulate into a functional component library with long-term utility. Instruction quality exceeds freely available online tutorials and documentation, and subscription cost remains below the amortized equivalent of purchasing permanent platforms. In practice, few subscription services meet these criteria. A $35 per month electronic subscription over 24 months costs $840, enough to purchase an Arduino starter kit at $90, Raspberry Pi 400 at $100, complete electronics component set at $150, and basic oscilloscope at $200, with $300 remaining for consumables and expansion modules. The permanent equipment delivers unlimited projects over 4 to 6 years versus 24 predefined activities that leave no residual capability once the subscription ends. Let's wrap up with some frequently asked questions. What specific skills should 10-year-olds learn from STEM toys that will matter for future careers? 10-year-olds should master text-based programming syntax in Python or C++, parametric CAD modeling with dimension-driven design, circuit analysis using Ohm's law and voltage dividers, systematic debugging methodology for multi-component systems, and technical documentation interpretation, including datasheets and API references, all of which directly transfer to entry-level capabilities in software development, mechanical engineering, electrical engineering, and systems integration roles. How do I know if a STEM toy teaches transferable skills versus just being educational entertainment? Check whether the product uses industry-standard software environments like Arduino IDE or Python rather than proprietary visual interfaces, outputs files in universal formats like STL or G-code rather than locked ecosystems, accepts standard expansion components following published specifications rather than requiring brand-specific modules, and provides API documentation or technical specifications rather than just assembly instructions. These characteristics indicate the tool teaches authentic workflows used in professional technical fields.
Can 10-year-olds really learn text-based programming, or do they need block-based coding first? 10-year-olds can learn text-based programming directly if instruction proceeds incrementally through syntax patterns, starting with simple programs that produce immediate visible outputs like LED control or servo movement, using IDEs with syntax highlighting and autocomplete to reduce memorization burden, and focusing on reading and modifying existing code before writing from blank files. Though hybrid environments that show blocks and corresponding text simultaneously can accelerate the transition for learners with prior visual programming experience. What's the minimum budget for STEM toys that actually teach career-relevant skills to 10-year-olds? A functional minimum investment of approximately $200 to $250 covers an Arduino starter kit for programming and electronics fundamentals at around $90, a basic breadboard component set with multimeter for circuit work at around $60, and either a Raspberry Pi kit for software-focused paths at around $100, or entry-level 3D printer for fabrication-focused paths at around $200. This baseline supports 2 to 3 years of skill progression before requiring significant expansion, making it substantially more cost-effective than monthly subscription services that accumulate to over $720 during the same period. How long does it take for a 10-year-old to progress from beginner STEM toys to using actual professional tools? With consistent practice of 3 to 4 hours weekly, learners typically transition from guided Arduino projects to writing custom code for original hardware projects within 6 to 8 months. From Tinkercad to Fusion 360 CAD with assembly constraints and engineering simulation within 8 to 12 months, and from breadboard prototyping to designing PCBs in KiCad within 12 to 18 months. Though these timelines compress significantly when projects integrate multiple skill domains simultaneously and expand when learners work in isolation without access to technical mentorship or troubleshooting resources. Do STEM toys for 10-year-olds need ongoing subscriptions, or can they function as one-time purchases? Quality STEM toys for 10-year-olds that teach real skills should function as one-time purchases with no mandatory subscriptions, as the goal is building capability with industry-standard tools that remain relevant for years, rather than platform-specific skills that expire when subscriptions end. Though optional cloud services for project sharing or community features can add value without creating dependencies, learners should prioritize products that work fully offline using standard file formats and widely available software to avoid vendor lock-in and ensure continued functionality independent of company survival or changing business models.
What safety considerations matter when 10-year-olds use real engineering tools versus toy versions? Real engineering tools introduce legitimate safety requirements, including eye protection when working with breadboards where component leads are under spring tension, supervision during initial 3D printer operation to establish safe bed and nozzle interaction protocols, proper soldering ventilation and temperature-controlled iron handling, circuit current limiting to prevent component overheating, especially with lithium batteries, and workspace fire safety equipment rated for electrical fires, all of which should be framed as professional safety practices used in actual engineering environments rather than restrictions, teaching learners that capability expansion comes with corresponding responsibility for risk management and proper tool handling protocols. Products that teach real skills introduce learners to the same tools professionals use daily. Arduino IDE for embedded systems development mirrors professional firmware engineering workflows. Python syntax learned on Raspberry Pi transfers directly to data science and automation engineering roles. Parametric CAD modeling in Fusion 360 teaches dimension-driven design used throughout mechanical engineering. And breadboard circuit prototyping develops troubleshooting methodology applicable to PCB design and electronics manufacturing. This ensures that skills compound over years of practice rather than requiring complete relearning when transitioning from educational tools to professional environments. To summarize, STEM toys for 10-year-olds that teach real skills create measurable progression toward employable technical capabilities rather than isolated educational activities. The optimal product portfolio combines text-based programming platforms compatible with industry-standard IDEs, CAD to manufacturing workflows using open file formats and universal tool chains, electronics prototyping with discrete components requiring circuit analysis, and robotics systems supporting authentic control theory implementation. Initial investment of $400 to $800 in permanent infrastructure delivers 3 to 4 years of capability development across programming, mechanical design, electronics, and systems integration, competencies directly applicable to software development, engineering, and technical roles increasingly required across all professional sectors. Prioritize products with explicit compatibility specifications, offline functionality, expandability using standard components, and clear pathways to professional tools to ensure learning investment compounds over time rather than dead-ending in proprietary ecosystems.
That wraps up this episode of the STEM Lab podcast. Thanks for listening all the way through. We're back every Monday, Wednesday, and Friday with new episodes. If you found this one helpful, I'd really appreciate it if you could leave a 5-star rating and write a quick review. It's honestly the best way to help other people discover the show when they're searching for this kind of content. And if you haven't already, hit subscribe or follow so you get notified the moment new episodes drop. See you in the next one.